Okay, so let's get started. So, of course, you had the midterm on Thursday, and I'm still grading those, but I expect to be finished sometime this afternoon. So, yeah, just keep on the lookout for that. The grades will be posted on Gradescope at some point. And there's also gonna be like in Gradescope you can leave feedback. So whenever I have feedback to give, I'm adding that in there. So do have a look through that whenever you get your midterm score back. Okay, so we're sort of shifting gears, although not really. So we're going to start talking about limits, but we're going to define them using the technology for collapsing collections that we built up. But I wanted to pause and show you this drawing that has appeared in the textbook and just sort of like show you the map of where we are and where we're headed. So we started off here and we talked about numbers and sets and functions. And then we spent a long time on collapsing collections and talked about their images and wrappers, and then got to continuity, which is sort of our first little peak here on the hike. So so now we've gotten past this and we're heading into limits. And we'll spend a little bit of time here. And once we've done that, there's sort of two mountains that we have to climb. So one of those is going to be the average value function or the derivative. And there will be a bunch of things to see along the way here. And then sort of the other one will be Riemann sums and integrals. So once we get through limits, we're gonna go left and do derivatives. You could really do either one first, but sort of traditionally you do this one first. And then we'll go into integrals, and then sort of at the end of the course, we'll get to the castle, which is the fundamental theorem of calculus. It sort of like tells you how these two things are related. Okay, so that's sort of where we are and where we're headed. So this week we'll be talking about limits. And this sort of addresses the question of what happens when a function isn't defined at a certain value, or how do you formalize the idea of like what values is the function approaching? So what happens if a function isn't defined at a value? And what can you say about the value that the function approaches? So we're going to quantify that today. So the idea is if you have, let's say we draw the graph of a function and it has some kind of hole in the graph, what can we say about like what is the like sort of what is the coordinates of the hole, right? What like what value would we need to stick in there to fill in that hole? Okay, so what we're gonna do is start with one-sided limits, and that will give us a way to define the limit as a whole. So basically, we're gonna take x values, sort of getting closer and closer to the whole, but just from one side, and say what values the function takes on along those numbers. Okay, so I'll just give you the definition and then we can do some examples. And this will feel sort of familiar to the stuff we've been doing with continuity, and I'll explain the connection later on in this lecture. So let's make a definition. So we'll say that the limit as x approaches some value a, and I'm going to put a little plus up here just to say that it's approaching a from the right side. So we're approaching, so if this is, say this is our value a, then x's are approaching a from the right, is what that little plus means. The limit as x approaches a from the right of f of x. So we'll say that this quantity is equal to L if, and we're going to define this with collapsing collection. So how this is going to work is we're going to take a one-sided collapsing collection for A, right? So we'll be zooming in closer and closer to the value A. And then what we want to see is that the wrappers of the F images of that collapsing collection form a collapsing collection for the number L. Okay, so we'll say, so let me write all that down. So if given a right-sided collapsing collection, for A, the wrappers of the F images form a collapsing collection containing the number L. Right, so a collapsing collection can only contain at most one number. So if that number is L, then that means that this limit is equal to L. Okay, so in the picture, this sort of like the coordinates of the whole, so it would have y value L, right? So this would be A comma L. Okay, so similarly, we're gonna make a definition for a left-sided collapsing collection, so taking the limit as x approaches from the left. So to do that, so all in red, so this will be the definition for limit as x approaches a from the left. So you just put a minus there. So I'm just going to make adjustments to the original definition. So it'll be if given a left-sided collapsing collection for A, the wrappers of the F images form a collapsing collection containing the number L. Okay. Okay, is this making sense? Hopefully this kind of fits with your intuition with what we've done with collapsing collections so far and continuity. But let's do an example. So, okay, before that, I'll give you like sort of the steps of how we would go about computing a limit, a right-sided limit. So here's like how to compute it. So these are just going to be steps similar to the steps that we had for showing that a function was continuous. So the first step is that we have to give a right-sided collapsing collection. collapsing collection for A. So let's say this is C1, C2, C3, and so on. Then the second thing that we need to do is find the images. So find f of C1, f of C2, f of C3, and so on. And then we need to find the wrappers. And then we need to check whether or not these wrappers of the F images themselves form a collapsing collection containing some value. So step 4 is, are these a collapsing collection containing some number L? And if the answer is yes, then we have that the limit as x approaches a from the right of f of x is equal to that value L. And otherwise, so if there's no number contained in this collapsing collection, then we say that the limit does not exist. And maybe I'll say as like an aside, it could be infinity, and we'll either today or Wednesday we'll say what that means. So just ignore this little parenthetical for now. Okay, are there questions about this before we do an example? Yeah.
So it could be either that they don't contain L or that it contains too much, right? Like it's not a collapsing collection.
Yeah. Yeah. Right. So like if it's collapsing to an entire interval, for example, then yeah. And the example that we're gonna do will be like that. So we'll do like well,
Like erratic, for example.
yeah. Other questions? Okay, let's do the example. So I'm gonna do the jump discontinuity function just so we can see something that's different when you compute the limit approaching from the right versus approaching from the left. So this will be j of x is equal to 2x when x is less than 3 and 2x plus 2 when x is greater than or equal to 3. Okay, so just to draw the graph of this function. Okay, so let's say this is x equals 3. So it's 2x and then it'll be 2x plus 2 at some point after that. So something like that. The slope is really, it's not to scale, but so we have this line, and then at some point it jumps up to higher line. Okay, so we're going to find the limit as x approaches 3 from the left of j of x. By the way, like here's how I remember that the minus corresponds to limit from the left versus the plus being limit from the right is like, the minus means that I'm going to take values that are less than 3. Right, so like, I'm looking at numbers that are to the left of 3 versus if I had the plus, that would be numbers that are more than 3. It's like that. Okay, do we have a guess as to what the limit as x approaches 3 from the left would be? Yeah. So it's just going to be one number. So it's like, what is the function? What values does the function approach as I put in things that are like coming from numbers, x is getting closer and closer to 3. Yeah.
36.
Yeah, so let's guess that this is going to be 6. So basically, how did we get here? So when I plug in numbers coming from below 3, so less than 3, I'm in this case of the function, right? The function's equal to 2x. So as I get closer and closer to 3, the outputs should be getting closer and closer to 2 times 3, which is 6. And then, like, we'll compare this to the limit as x approaches 3 from the right, which will be taking values of x that are getting closer and closer to 3, but now from numbers that are greater than 3. So we'll be in this case. And here, the guess will be that the limit is 8. Does that make sense? So today, I'm gonna show you how to arrive at this conclusion using collapsing collections, but later in the week, we will get sort of like more systematic tools for just calculating these things that we won't have to do collapsing collections every single time. Okay, so the first step is that we have to pick a left-sided collapsing collection for 3. Right, because I want to see what happens when I plug in intervals that are getting smaller and smaller, sort of getting closer to 3. So for this, I'll just do the standard left-sided one for 3. So the right endpoint of all of these intervals is just going to be 3 all the time, and the left endpoint will get closer and closer. So this will be 3 minus 1. Next interval will be 3 minus 1/2. And then 3 minus 1/3. And so on. Okay, so the left endpoint of each of these intervals is getting closer and closer to 3. Okay, so what are the F images of these intervals going to be? So if I draw a little sketch, so let's say I want to compute the F image of the interval, let's say a comma 3, because they all have the right endpoint 3. So I'll put in this interval where this left endpoint is a. Then what I'm looking at above that is going to be something like that. And these values are all in this first case of the function, right? We're only plugging in numbers that are less than 3. So every number in this interval just gets multiplied by 2, right? And so the interval in the output will have as its lower endpoint, that'll be 2a. And up here we'll get values getting closer and closer to 2 times 3, which is 6. So the image of an interval a comma 3. So if I apply f to this, this would be 2a comma 6. Does that make sense? So the images become 6 minus 2 comma 6, 6 minus 1 comma 6, 6 minus 2/3 comma 6, and so on. Okay, are there any questions about that step? Okay, so then the wrappers. Of course, these are just going to be taking the open parentheses and making them closed in this case, because these are all just open intervals. We got 6 minus 2 comma 6, 6 minus 1 comma 6, 6 minus 2/3 comma 6, and so on. Okay, so step 4, is this a collapsing collection containing some number? And what is the number?
6.
Yeah, so for sure 6 is in all of these, right? Because you can see the right endpoints are always 6 and it's a closed interval. So 6 is in there. Why is this a collapsing collection? Yeah.
Because it's collapsing from the left side. It's like every interval is contained in the
Yeah, so every interval is contained in the previous, and then, you know, if I had, any other number that's not equal to 6, eventually it's gonna be excluded by some interval, right? Because these left endpoints are getting, as close to 6 as we like. Okay, so this is a collapsing collection containing 6. So the conclusion is that the limit as x approaches 3 from the left of this function j of x is equal to 6. Okay, are there questions about that? Are we convinced that if we did this for the right-hand limit that we would get 8? Yeah, so in this step, so we would pick a collapsing collection where 3 was the left endpoint of the interval and the right endpoints were getting closer and closer to 3. And then the images now would come from this part of the graph, right? So if I had intervals like this, we'd be looking at the second case of the graph. And so you would get these green intervals would be a collapsing collection, the wrappers of them would be a collapsing collection for E. Okay, so one thing is that we calculated these limits, one from the left and one from the right, and we got 2 different numbers. So, and that's, I mean, if you think about it, that's kind of like why this function is not continuous, right? Is like it had the left and the right limits did not agree with each other, right? So that sort of tells you that at that point I have to pick up my pencil to draw the limit, or sorry, to draw the function. So this is sort of just like previewing how this is going to connect back to continuity. So I'll give you one more definition about limits. So we'll say that the limit as x approaches a of f of x is equal to L. So now we don't have any plus or minus here, so just like the limit as x approaches a. So this is gonna be if the left and the right limit both exist and they're equal to each other. So we'll say this if both the left and the right exist and equal L. Okay, so this was not the case in our example, right? The left limit and the right limit did not agree with one another. So we don't have just a single value for the limit as x approaches a. But if we did have that, then you could write this. Okay, so let's talk about how this relates to continuity. So how do these two things relate to each other? The process that we're going through to decide whether or not a limit exists feels very similar to the process that we went through to decide whether or not a function is continuous at a point, right? So I'll write down a fact and we can convince ourselves of this, but maybe it won't be surprising. So here's the fact. A function f of x is continuous at a if and only if, which I'll come back to this phrase, if and only if, the limit as x approaches a of f of x is equal to the value of f of a. Okay, so what does if and only if mean? So this phrase appears pretty often in like math contexts. And what we mean by if and only if is that these two statements are equivalent. So if a function is continuous, then it holds that the limit as x approaches a of f of x is equal to f of a. And if this is true, then that also implies that f is continuous at that point. So let me write down what this means. So, if f of x is continuous at a, then the limit as x approaches a of f of x is equal to the value f of a. That's one thing. Second thing, if the limit as x approaches a of f of x is the same thing as just plugging in a to f, then f is continuous at a. So the way that we will use this most of the time is this way. So if I ever ask you, what is the limit of this function, and you know that the function is continuous everywhere, then you can just plug in the value to find the limit. Does that make sense? So, like there's functions that we proved are and aren't continuous, and so you can, if you wanted to compute the limit, as x approaches any value of that function, you just plug in the number. And this one, I think helps us just understand the relationship between limits and continuity, right? So in our previous example, we had that, you know, the limit as x approached a from the left did not agree with f of a, right? Because we got 6, but f of a was equal to 8. And so that tells us that the function was not continuous at that value. Is this making sense? How these two things are connected? Other questions? So maybe let's just check this on some examples that that we've looked at. So let's like check this statement on some examples. So one function that we've been looking at is L of x is equal to 2x. And we showed that this was continuous everywhere. And so from that, we get that, for example, the limit as x approaches 3 of L of x is equal to the number L of 3, which is 6. And if I draw a little picture, this should match our intuition about what limits are doing. Right, so it's making sense, like this, we know this function is continuous, and so the limit as x approaches 3 from either side is going to equal 6, which is also the value of the function at x equals 3. Let's look at, so yeah, just to write this down explicitly, the function that we were looking at in the previous example, j of x, so we got that the limit as x approached 3 from below, from the left, oops, it's not called f, it's j. So we got 6 for this. And 8 for this. And so since the limit from the left and the limit from the right are not equal, that tells us that the limit as x approaches 3 of j of x does not exist. And then going back to the statements that we had, from that we can conclude that the function is not continuous. So this tells me the limit as x approaches 3 of j of x does not exist. You can write DNE, so what people do a lot of the time. So this limit does not exist, and so j of x is not continuous. At x equals 3, which we had like previously verified just directly from the definition of continuity and collapsing collections. Okay, how would this work for a removable discontinuity? So let's think quickly about this function r of x, where we have the value 2x when x is not equal to 3, and 9 when x is equal to 3. Okay, so what would the limit as x approaches 3 from the left of r of x, b. And same thing for limit as x approaches 3 from the right, rx. What would these limits be? So if I plug in a collapsing collection here and take the wrappers, what value would it get? Yeah.
Wouldn't three from the left be six, and then also three from the right?
Yeah, so we would, exactly, so we would get 6 for both of these. Here's maybe one way that you could see this. For all of the numbers that I'm plugging in with the collapsing collections, we're going to get the same things as we would for just the function 2x. Right, so like my collapsing collections are always avoiding the number 3. So when I plug into the function, I get the same behavior as if this was my function. And so and since that function is continuous, I should get 6. Yeah.
The reason the removal is this computational value doesn't screw up the set of all the wrappers is just that it's not just because you're doing 2 separate left and right sided collapsing collections.
Yeah.
Which again is open intervals, therefore not including x equals 3.
Yeah.
Sort of never makes it in to the F images and therefore the wrappers of the F images.
Exactly. Yeah, yeah. So right, so our collapsing collections on the x-axis are always avoiding this number 3. So we will never get this guy in our F image, and therefore it will also never be in the wrappers. Okay, so this limit does exist now. So we get limit as x approaches 3, rx is equal to 6, right? Because these two numbers agree with one another. But this number is not equal to the value of the function at x equals 3, right? Because this is 8. So that means that the function is not continuous. Does that make sense? Oh yeah, sorry. So just to recap that, so the limit from the left equals the limit from the right, and they both equal 6. So that means that the limit as x approaches 3 is equal to 6. So the limit exists and it's equal to 6, but this number is not equal to the value of the function at x equals 3. So that means that the function is not continuous. Okay, are there questions about this? Okay, so let's go back to dealing with infinity. So there's going to be sort of 2 things to deal with here. One is what happens if I plug in, or I start plugging in numbers and the function itself approaches infinity. And the second one is going to be asking what happens to the function as my x values go to infinity. Right. So so let's do the first one. So we'll do infinite limits. Okay, so let's consider this example. So we're going to look at the limit as x. So x values for now are just going to still approach a number. So x is going to approach 0 of the function 1 over x squared. So as x is approaching 0, what are the values of this function doing? Yeah. Yeah, they're getting huge, right? So let's just plug in a couple of values. So let's say, so let's look at what happens for some x values and then what happens to 1 over x squared. So I'll plug in 1, 1/2, 1/3, and we'll just see what happens to 1 over x squared. So 1 over 1 squared is 1. When I plug in 1/2, I'm going to take the reciprocal and square it. So I get 4. And then here I'll get 9. So let's say down the line, I'm plugging in like 1 over 100. Then here I would get 100 squared, right? So like as you plug in smaller and smaller numbers here, we're getting huge outputs. So then in this case, it makes sense to say, so intuitively, we want to say the following, that the limit as x approaches 0 of 1 over x squared is equal to infinity. By the way, I was only plugging in, positive x values, but since we have the squared here, if I plugged in the negatives, I would get the same thing. So you put a plus or minus here. We get the same outputs. Okay, so we're gonna write a definition using collapsing collections. And at this point, I feel like you can almost guess what the definition should be. So while I set this up, just think about how you might define this using collapsing collections. So what we're gonna do is plug in a collapsing collection or a one-sided collapsing collection for the value we're approaching. So in this case, it was 0. And then on the other side, we want to see a collapsing collection for infinity. Right? So we'll say that the limit as x approaches a from the right of f of x, we'll say that this equals infinity if when we apply f to a right-sided collapsing collection for A and take the wrappers, we get a collapsing collection for infinity. Okay, it's been a while since we defined all of the different flavors of collapsing collection, so let's just remember for a second what a collapsing collection for infinity is. So let's recall. So a collapsing collection for infinity is going to be one where the right endpoints are all infinity and the left endpoints are just numbers that are getting larger and larger. So a collapsing collection for infinity is one which has all right endpoints equal to infinity. So as an example, this could look like 1 comma infinity to, oops, and you never write closed bracket here, just by convention, because infinity isn't like a number, it's just a symbol. So 2 comma infinity, 3 comma infinity, and so on. And then second thing, of course, we'll also just have the same definition for the limit as x approaches a from the left. So again, in red, we have limit as x approaches a from the left, f of x equals infinity, if we just swap out this right-sided collapsing collection with a left-sided. Okay, maybe I'll pause for questions if we're adding more footnotes to this definition. Other questions? Okay, more footnotes. So if the limit from the left and the limit from the right agree and they're both infinity, then we have the limit as x approaches a of f of x is infinity. So if the limit as x approaches a from the left of f of x equals infinity, and the limit as x approaches a from the right f of x equal infinity, then we have just the plain limit as x approaches a f of x equals infinity, just as you might expect. And then the last footnote is that we can also make this definition for minus infinity. So in pink, the limit as x approaches a from the right f of x equals minus infinity if, when we apply f to a right-sided collapsing collection for a and take the wrappers, we get a collapsing collection for minus infinity, which now would look like this: minus infinity, comma 1, minus infinity, comma 0, minus infinity, comma minus 1, so on. Okay, so that was a lot, but hopefully it fits into the framework of limits as we've set them up so far. So this is just kind of how to deal with the case when the limit as x approaches a number is infinity. So I'm gonna stop there for now. We'll do an example of an infinite limit at the start of class next time. And otherwise I'll see you on Wednesday.